Hello students, let us now begin lesson 3b. This corresponds to the starting point of chapter 2 of our textbook. It fell right in the middle of week 3, so I divided into 3a and 3b. Let's begin. Lesson 3b, graphs. And the first concept is the coordinate plane. There are multiple ways to represent points on a plane, and one way to do that is to associate each point with a pair of real numbers, x, y, where x is the rightward distance from the origin and y is the upward distance from the origin. Here are 4 examples: blue, red, green, and brown points. From the origin here, where my mouse is, 3 units to the right and 2 units up. That's how I get 3, 2, x, y, rightward and upward. How about the red points? From the origin, 3 units to the left and 1 unit up. Or equivalently speaking, negative 3 units to the right, because x is rightward distance and getting a negative of right is going left. So 3 units to the left is the same as negative 3 units to the right, and then going 1 unit up. How about the green point? From the origin, negative 2 units to the right, or equivalently 2 units to the left, and then negative 3 units up, the same as going 3 units down. And likewise, we have this brown point. For simplicity, I have only integer units, but I could have selected any pair of real numbers. So this could be, instead of 3, I could have selected, say, pi, 3.14 something. This kind of system is called rectangular coordinate system or Cartesian coordinate system. And the plane equipped with Cartesian coordinate system is called Cartesian plane or rectangular coordinate plane or simply coordinate plane. The reason it is called rectangular coordinate plane is rather simple because you can see a bunch of rectangles here. Blue rectangle, red rectangle, green rectangle, and brown rectangle, which happens to be a square because horizontal and vertical distances are the same. In general, we have rectangles. That's why it is called rectangular coordinate system. As for the name Cartesian coordinate system, it is named after French mathematician and philosopher Descartes. On the Cartesian coordinate system, we can divide a coordinate plane into 4 parts like this. Quadrants 1, 2, 3, and 4, where quadrant 1 has both x and y positive, and quadrant 2 has x is negative, y is positive. Quadrant 3, x is negative, y is negative, and finally quadrant 4, x is positive and y is negative. Quadrant 1 and 4, x is positive, so I'm moving to the right from the origin, while quadrant 2 and 4, x is negative, which means I'm moving to the left. How about y coordinate? From the origin, I'm moving up, so quadrants 1 and 2 have positive y coordinate, and quadrants 3 and 4 have negative y coordinate because I'm moving down from the origin. The next concept is the distance formula, and it comes from Pythagorean identity, so it's actually easy if you associate a picture. Without the picture, this formula may look really complicated and it may be difficult to memorize. But if you associate it with a picture, now everything makes sense. We have 2 points, P1 and P2, where P1 is x1, y1, and P2 is x2, y2. And we can associate a right triangle like this. And we have hypotenuse squared is equal to horizontal squared plus vertical squared. And horizontal squared, that is difference of x coordinates squared. Vertical squared is difference of y coordinates squared. And thus we have this green squared plus blue squared. And then we want the distance itself, not the square. So take the square root of that, and there goes the distance formula. It may be a bit difficult to memorize all this, but if you look at the picture, then you can easily deduce it from the Pythagorean identity and then take the square root. Okay, let's move on. I don't think this one is still worthy of significant class time. The next one is pretty simple too, the midpoint formula. Simply take the average of x-coordinate and y-coordinate, and here's a graphical justification. Average of x-coordinates, so in terms of x-coordinate, horizontally in the middle, and average of y-coordinates, so vertically also in the middle. So that's the midpoint formula. Picture is nice, but even without the picture, it makes a lot of sense. Simply take the average of the two. Finally, internal section point. And this one may not be that important, but it appeared in our textbooks, so I'm mentioning it. Also, it is discussed in MyMATLAB as well. So a special case when we have division by here's the internal section point formula. Suppose that we have this kind of subdivision, 1 unit versus 2 units there. So this distance to the right is twice as long as this distance on the left. So plug in m is 1 and n equals to 2 into this formula. That's the internal section point B. This program is randomized, so let's run it again. And this is 3 to 1, so that's 3 units versus 1 unit. Again, plug in m equals to 3 and n equals to 1. Run it, and then you're going to get the internal section point. By the way, if m and n are the same, 1 to 1, then this formula is identical to the midpoint formula there. Because m plus n is 1 plus 1, that's 2, and then numerator we have 1 and 1, so we have this formula directly. These are a little bit more general cases. 5 to 3. If I run this, okay, all right, 2 to 2, so 2 unit versus 2 unit. Basically, it's 1 to 1. I just repeat it until I hit the midpoint formula. External section point. Instead of addition, we have subtraction, and then we have external section point. Distance from P to P1 is 2 units. From P to P2 over here is 5 units. So 2 to 5 externally, and you can get it from this formula. But this one is not that important, so let's just move on. As a matter of fact, I have to say entire section 1 of this notebook is not that important. Not really worthy of class time. I'll just show you the distance formula and the midpoint formula just one more time. And then let's just move on to section 2. Okay, section 2. Graphs of equations. A graph of an equation of two variables is an example. We have an equation, algebraic equation, with two characters, x and y, where x corresponds to the x-coordinate, the horizontal distance from the origin, and y is the vertical distance from the origin. Then often you're going to end up with a curve, or as you can see in this case, multiple pieces of curves. And then these are not curved segments, by the way. They don't stop, they just go on forever. As you can see, it's stopped by the frame. It'll just go on forever. In any case, whenever you have an equation of x and y, it's likely that you're going to end up with a curve. Now here are some interesting questions. Is the point -1, 1 on the curve, which I just highlighted in blue? Second question, is the point 1, -1 on the curve? How do we check? As a matter of fact, what does this equation tell us? This picture visualizes set of all points x, y that satisfies this equation. So if this point 1, -1, or this red point, satisfies this equation, then that's going to be on the line, on the curve, excuse me. If this -1, 1 satisfies this equation, then it's going to be on the curve. Let's check. Let's copy and paste this thing. And then let's plug in 1, -1. Excuse me, -1, 1. So from here, let's plug in. Let's plug this in. So how does it work? Let's copy and paste this thing. And then here I'm plugging x equals to -1. So that's -1, and that's -1, and y equals to 1. So that's 1. And that is 1. That is -1, and that's 1. Now, will this satisfy this equation? Is this true? Well, pick up your calculator and please check. If necessary, stop the playback and do your computation. While you're working on it, let me do my computation. So left-hand side turns out to be 4. And how about the right-hand side? Let me copy and paste it, and then let's do this computation with Mathematica. That 2 is 4. So what do we have? We have 4 equals to 4. Does it make sense? Yes, it does. 4 is equal to 4 is true. So what does that tell us? -1, 1 must be on this curve. Let me go back to this curve. -1, 1, -1, looks like it, right here. I'll show you the picture in a moment. How about the other case? In this case, basically we are doing this. And then let's erase this thing because I didn't check those yet. So in the same condition, let's check x is 1 and y is -1. See if that's true. Okay, so x is 1 and y is -1. X is 1 and y is -1. So is this true? Will 1, 1, -1 satisfy this equation? Left-hand side is 4, and the right-hand side, let's check this computation. You can do it with your handheld calculator too if you want to. And that's -2. So the conclusion we get from here is (4) equals to -2. Does it make sense? No, it doesn't. So the conclusion, 1, -1 is not on this curve. I can check this with other points too. If given point is on a curve or not, how do we check? By plugging those in. By the way, here's a solution, the same thing we just did, and it comes with a visualization here. 1, -1, and the red point is not on the curve anywhere. -1, 1, the blue point is on the curve, yes. 4 equals to 4, yes, that's true. 4 equals to -2, that's not true, no. That's how the equations and points are associated. Looks like we'll have to resume intercept and other examples in the next video. Let's stop here. See you again shortly.